start. Okay, hello everyone. So it's a great pleasure to introduce Andre Mesinger today as a first colloquial speaker of the year. So we're going to have these colloquia once per month throughout the year now. Andre did his PhD at the University of Columbia under the supervision of Sultan Heyman, who happened to be who was visiting last week, as you know.
Next, you have to have one of my students come.
Exactly. So after his PhD, which was, I think, in 2006, Andre went to Yale as a postdoc and then to Princeton as a Hubble Fellow before he started a professorship position at the Scuola Normale in Pisa. And Andre is one of the leader of the field of cosmic reionization. He is particularly well known, and I'm saying this mainly because this is still the Institute for Computational Science, and he's well known as being the author of the code 21 centimeter fast, which I guess was named after CMB fast, which the old people may still remember. I still use it. Actually, it was written by someone who used to be here at this institute but left a while ago, so the young people won't remember. But contrary to CMB fast, which is only used by some old professors, 21 centimeter fast is still very much in use and is actually the most popular code for cosmic dawn reionization in the field. And I'm very happy to have Andre here, and he's going to talk about the future of 21 centimeter cosmology.
Thank you very much, Harald. That was a nice introduction, and it's a pleasure to be here. And thank you for the invitation. Yeah, so I'm going to talk about the status and the future of 21 centimeter cosmology. I realized I omitted the during the first billion years part of the title when I submitted, because there's another field of cosmology that's at later times, which I won't have a chance to cover. So where to put this in context, this is a representation of the co-moving volume of our observable universe. I don't know which side to pick. I guess I'll pick this side, which was drawn to scale. It's something that was made by Cynthia Chang that I adapted here, such that the relative co-moving volume is represented by the relative surface of this sphere. So, you know, if we're here at the center, we've mapped out roughly using the BOSS and eBOSS. We mapped out the structures out to galaxies and structures out to redshifts of 3 or 4 or so, and then we see galaxies and some quasars out to redshift 5, and a few of them even out to redshift 10 or so. And then we have this beautiful CMB, which in reality is more like a 2D surface that's sitting there at redshift 1100, which marks the edge of our observable universe. So if we're here at the center, you know, we're in this, you can imagine we're in this room, and we see like the local environment, maybe the few meters around us, and we see the walls, and then the rest of this volume, which is over half of our volume, is almost completely dark to us. And so I'm going to be focusing on this half of the observable universe that's sitting there in the first billion years, which we've only had a few observations of. And this is really the birthplace of structure, the birthplace of galaxies, because these fluctuations that we see in the photon baryon fluid from the CMB start collapsing into dark matter halos. The baryons form stars, black holes. They start ionizing their surroundings, heating their surroundings, and their radiation spreads around. in the process of cosmic dawn, and eventually reionizes the entire universe. So this is the last major phase transition of our universe, and it's sitting somewhere in this first billion years. So as I mentioned, we have had a few observations, and recently there's tremendous progress that's been made by JWST that's observing individual galaxies. And so we make these kind of number counts of galaxies, and the deeper we go, this is still an old image from Hubble, but JWST hasn't gone to this depth yet. The deeper we go, it's still the deepest luminosity function. So these are luminosity functions. So it's the number density of galaxies as a function of their brightness per magnitude bin per megaparsec cube. And so these are luminosity functions at different redshifts. And the deeper we go, the more galaxies we find. And it's, an exponential trend. And so if you just make some simple estimates about where these galaxies should sit, you realize that we're really seeing the proverbial tip of the iceberg. Theoretically, we expect galaxies down to a UV magnitude of -10, but even the first galaxies that cooled by molecular cooling should be down here at even fainter magnitudes. And to make matters more stark, this iceberg is on a linear scale, but this axis is on a log scale. So we're really kind of just seeing the very few galaxies. So if you're a galaxy person, you're interested in studying, typical galaxies, it's as if you were, an alien and you're interested in humans, but you're only able to see humans based on their wealth. So you see a few people, but if you're trying to make statements about the general population, sure, you can say humans have on average one head, a couple of arms, a couple of legs, but you miss like the diversity of professions, races, and all of the wonderful things that make us human. Evil. All right, I haven't tried to be a little bit politically correct here, but okay. That's a valid opinion. Yeah, so the way the field is kind of progressing is that we get kind of direct studies of individual galaxies with these optical and infrared telescopes. But then the bulk of the galaxies, the 99.9% of them, we're studying through their indirect imprints in the intergalactic medium, which is where 99% of the matter lies. So we already know something about this intergalactic medium during these first billion years by measuring the epoch of reionization and kind of mean properties that we get from observations of using galaxies and quasars and the CMB and measuring how their light changes and gets absorbed and scattered as it comes to us. And so this is the current, let's say, state of understanding of the epoch of reionization. So it's the mean ionization state of the universe as a function of redshift with some observations. It's an incomplete estimate of observations. And the gray here is a result from a combination of various probes. So we know that reionization roughly had a midpoint of roughly at redshift 7 or so, and maybe there's a tail extending out to higher and higher redshifts. We also know something about the thermal history of the universe, although most of this comes from late times. But theoretically, we know that the mean temperature of the gas was thermally coupled to the CMB, but then when this became less efficient, it adiabatically cooled as 1 plus z squared, whereas the CMB continued cooling as 1 plus z until the first stars, the first astrophysical objects, we think were responsible for heating the universe to temperatures higher than the CMB, and then they get flash ionized by UV fronts to temperatures of 10 to the 4. So we have measurements here. We think that the first objects that were responsible for this upturn were X-ray binary stars and I'll return to that point later. Just on the basis of this is what kind of dominates the X-ray emissivity of local star-forming galaxies. But we don't have any measurements during this epoch until very recently, and I'll get to that later. So these are kind of mean evolutions, but there's so much more to learn. As I mentioned, this is half of our universe, and so if you know all we could say are 2 lines, that would be very sad. So the most powerful probe of this first billion years comes from this 21 centimeter line. So as you know, 21 centimeter line is the spin flip transition of neutral hydrogen. And so when the universe was predominantly neutral, we can see it in this line, and it happens to have almost a Goldilocks optical depth. So you might be more familiar with the Lyman alpha forest. Unfortunately, the forest saturates at very low neutral fractions because the optical depth is so large. But here, for a neutral gas, the optical depth is of order 0.01 or so for a gas element at these redshifts, which is something that we can relatively easily measure, at least from thermal to noise estimates. And so the way this works is you measure the difference in intensities of the gas against some background. In this case, the background at these frequencies is the CMB. And so lo and behold, the measurement that we're trying to make might hopefully look something like this. So we'd fill this gap of half of our universe and measure the intensity fluctuations which correspond to temperature, density, and ionization fluctuations. And so if you just zoom in on one of these slices, you get kind of a light cone where this is one on sky transverse axis, this is redshift. And you can see the beautiful richness of this signal, which comes from the fact that it is, you know, this nice optical depth. So it allows us to trace various terms. If you expand out to first order what this brightness temperature should be, it's something that depends on the neutral fraction of the gas density, redshift space distortions, and even the temperature. This is the CMB temperature. This is the gas spin temperature. So it has both astrophysical and cosmological terms. And so as you go to earlier times before there were stars, you mostly don't see a signal with some caveats as you go to higher redshifts. Then, well, okay, I'll talk about that later. And then you have the first stars driving the cosmic dawn, which end up coupling the spin temperature to the gas temperature. So you see the CMB, you see the gas against the CMB, and then these X-ray binaries or other X-ray sources heat the signal. So you see the cosmic gas in emission as opposed to absorption following that transition. And then you have reionization, which is this inhomogeneous patchy process that then erases eventually the signal. So how do you learn about these typical galaxies and other processes, including physical cosmology? Well, for galaxies, you know, it's really in the kind of the structure that I just showed, the timing and the structure of these signal. So the clustering of the typical galaxies weighted by their production rate of ionizing photons, emission rate of ionizing photons, results in different morphologies of this process. So even at the same stage of reionization, for example, if reionization was driven by these oligarchs, evil oligarchs, as someone put it, you would have bubbles that are characteristically much larger, correspond if it were more a democratic process with a bunch of small galaxies driving reionization. Similarly, you know, from the temperature term, you can say something about the first sources of X-rays in galaxies. So if these emitted relatively hard X-rays that have a long mean-free path, temperature fluctuations would be washed away. But if the mean-free path was very short, then you would have much larger fluctuations in the temperature, where regions that are close to galaxies would be heated up while regions further away would remain cold. There's the other more exotic sources of heating that we know much less about. These are kind of standard sources because we see them in local galaxies as being efficient emitters of X-rays. But cosmic rays could be a culprit if they manage to be formed in the first galaxies and then manage to escape them in sufficient quantities at sufficient energies that can couple to the gas. And so hopefully if this is a relevant process, maybe with different mean-free paths, we can, from that result in different patchiness of the heating process, we could say something about this source. Another, more exotic source are dark matter annihilations. This has been studied in several works. And you have very uniform heating in this case, so it's not degenerate with galaxy heating, and we can potentially disentangle the two using the spatial information here. There's also dark matter decay that could again uniformly heat the universe before the galaxies really had a chance to have a go at it. And so this was from a recent paper where we did Fisher estimates to estimate the constraints on the decay time scale, and potentially 21 centimeter could improve on current constraint by 1 to 3 orders of magnitude. Another really cool probe of cosmology comes from baryon acoustic oscillations. So you probably know what baryon acoustic oscillations are, but the usual way of thinking about it in terms of density contrast between the baryons and the dark matter is not as relevant at high redshifts. What is more relevant are the relative velocities that occur between the baryons and dark matter. This is the same underlying source. The baryons are kinetically coupled to the CMB, and so after recombinations, the dark matter decoupled earlier. So after recombination, there's both a relative density offset, but also relative velocity shift as these baryons now start seeing the dark matter. And so this gives a scale, the sound horizon. And so if you do numerical simulations of how this relative velocity impacts star formation, as you might expect, regions that have a large relative velocity get such. This is showing a zoom in on hydro simulations that have zero relative velocity. Well, yeah, zero relative velocities, 1 and 2, 3 sigma. And as you increase the relative velocity, you can already see that the baryons essentially are wind passing over the dark matter halos at early times. And so it's much more difficult to form stars in regions that have a large baryon relative velocity. And so as a result, because these are well-known acoustic oscillations that drive this, your 21 centimeter signal should have these nice acoustic features, which are completely, a clean measurement that cannot be mimicked in any way by astrophysics. So we could have essentially a relative, essentially a ruler, a cosmic ruler that can help in answering the Hubble tension questions at redshifts between 10 and 15, maybe 10 and 20. So that's a little hodgepodge quick of a lot of the interesting questions that we can answer. So I'll spend a few minutes on the current status. This is nice for the future. Right now, you might have heard that in terms of global experiment, there was this exciting claim of a detection by the EDGES experiment. Global experiments are very cheap, and so they're popular. You need like one small antenna, so you can fund them pretty easily and deploy them pretty easily. And this is an EDGES, the first EDGES experiment in the one that made the detection in Australia. And so they claim that they see this kind of surprisingly large dip with a weird shape at redshifts between 15 and 20. Yes.
So just based on the picture that you showed earlier, right? So would you expect to always see this kind of like going up first, that you go below first, right? And if you don't, then adapt differently, right? So
Yes.
expect to see something like this also, these kind of signals that they go down. And
Yes. Yeah. So it wasn't the thing that was surprising wasn't the fact that there was a dip. We all expect that there's a dip, because if you just do an estimate based on the efficiency of heating versus the efficiency of ionization at a fixed star formation rate, assuming locally calibrated sources, it's 10 times more efficient to heat the universe to temperatures above the CMB than it is to ionize it. So you expect that there's this process earlier, like in the light cone that I showed, where the universe is heated before it's ionized. So it goes down and then up in a sense. The thing that was surprising is the level of this. So in standard scenarios, you have a fixed amount of contrast that you can have based on the fact that post-thermal decoupling, the gas goes as 1 plus z squared and the CMB goes as 1 plus z. And so that gives you the maximum dynamic range that you can have. And this is, a factor of a few larger than that range.
but that there was, and we can argue the specific history of the organization that.
Yeah. I mean, you would push reionization over here. So that's not as worrisome. These is like at the edges of the band. The way, in general, looking at the signal in this way is very, very misleading, because this depends on how everything is parameterized, which is why global signal experiments are very difficult to do, because you throw in your parameterization of your foregrounds, your instrument, systematics, cosmic signal, and then you do a inference with everything there, and you have to know everything to extremely high precision and put priors on them and extract it. So this is essentially a few of the best fits, which does not tell you about the whole posterior. But even so, you don't know too much about the edges here, because this is like the entire band. So they're fitting things that go like this, and so this is a result of the basis set they're using. No worries. A couple of years ago, though, there was another experiment called SARAS, which is completely different. It uses this parabolic antenna that's floating on a lake, with the idea that the ground, the systematics that you get from ground plane reflections, ground reflections, are decreased in this case, and they see no evidence of this signal. And so there's still contention on the global community. I won't discuss this further. Again, it's a very difficult thing to measure, because you have one measurement, and so you can't use data analysis things where you say, well, statistically that region of the sky has to look like that region of the sky to help you distinguish between cosmic signal and foreground. So you really have to know all of the things that are in your signal chain to extremely high precision. What I will talk about are interferometers, and I think this is the potential, right? So this is where we get this beautiful map that's going to eventually win the Nobel Prize, right? This there's a first generation of instruments that are already taking data, going from MWA in Australia, LOFAR in Europe, GMRT in India, and HERA in South Africa. These three are really the three that are coming out with ever increasing data. But it's a hard measurement, still a hard measurement, because you're still limited by foregrounds and systematics, and the cosmic signal is sitting under foregrounds, predominantly our own galaxy, that are 3 to 4 orders of magnitude stronger. If you're in the CMB community, you say, okay, well, that's nothing. 3 to 4 magnitudes is nothing. But you know, there are other challenges, including systematics, that limit this in this case. But the hope is for interferometry to measure the cosmic signal in a so-called EOR window, because foregrounds, our own galaxies, they're essentially a synchrotron emission that is smooth in frequency. So you get structure in the on sky plane. This is, by the way, cylindrical power spectrum. So this is these are modes that are on sky, and these are modes that are along the line of sight. And so the foregrounds really are limited. They don't have much structure along the line of sight, so they're limited to down here, which is large scales along the line of sight. But then, because the instrument response is not the same with frequency, there's a spillover called the wedge. But there should be a clean window here at reasonably small line of sight modes that allows you to measure reasonably well the signal without contamination. That's something that we see in simulations. If you look at what the EOR signal looks like in this 2D power spectrum and what the foregrounds look like, and the combination of two, you can see that in this EOR window, it does trace the EOR more than the foregrounds. So modeling it is also hard. I don't want to focus a little bit on observations, but you know, I'm a theorist at heart. But yeah, modeling of this is very challenging. So if you start with, this is a light cone of the density field. So you identify from the density field where galaxies are supposed to sit. These galaxies emit radiation in various bands. And all of these, because it's such a physics-rich signal, you need to trace radiations in all of these bands. This include Lyman alpha, Lyman Werner, X-ray, ionizing. They all have different mean-free paths, and so it's challenging. You can't use the same algorithms for both. And then this radiation actually has feedback on the galaxies themselves, because it heats and photodisassociates H2. It heats the gas, which suppresses star formation. And so all of this has to be kind of self-consistently modeled. Why is this not moving? It's just slow. To get finally the 21 centimeter signal. But at the end of the day, so it's challenging to model. You need to be, let's say, efficient. But at the end of the day, you get this rich signal here, which traces different processes at different times. So you can see here it traces the molecular cooling galaxies, which are modulated by initially Lyman Werner feedback, X-ray heating here. You can see ionization here at late times. So at different cosmic times, you're tracing different physics, which is why the signal is so rich. So as I said, measurements are improving, but currently we only have the upper limits on sorry. And so this is a compilation that's already a bit out of date on the power spectrum upper limits at this kind of K mode of 0.1, which is in that cylindrical power spectrum, kind of at the edge that I showed earlier, kind of at the edge of where the foregrounds sit. This is kind of the sweet spot, because as you go to smaller scales, higher K, your thermal noise starts being a problem. As you go to larger scales, smaller K, your foregrounds start dominating. So it's at that edge that it's most easiest to get measurements. And so we're still a couple of orders of magnitude away from where we think the signals are, which are down here. But interestingly, even with being, you know, upper limits a couple of orders of magnitude away, we can still say something new. And I'll spend a few minutes talking about that. And I'll focus on these two data points that were made by the Hera collaboration, which I'm a part of. It's US led, but it has global collaboration, and it's an instrument that's in South Africa. And so Hera, in its first observing campaign, with just a preliminary set of antennas, 39 out of the total 350. observed 3 fields. It doesn't point, so it just looks up in so-called drift scan. So you can see our galaxy going like this. And so we measured in these 3 fields the cosmic signal, and the cosmic signal should be the same in all 3 fields. So we looked at the power spectrum that we get as a result. And so these are the 3 fields. These are 2 bands. One is at redshift 8, the other one's at redshift 10. And you can see the spectrum measurements here in pink, and the thermal noise estimate here is in black. So the takeaway here is that the data here lies mostly on the thermal noise in these bands, except for large scales where there are some residual systematics and foregrounds. So it means we essentially detected the noise. If we detected the noise, that's like saying that there's no signal above that limit. But then you can ask, well, what? Okay, so there's no signal above that limit. So what can we rule out, right? What are the models that sit above that limit? So, i.e., what are the models that have the largest power? That would be the easiest to rule out. So if you go back to this equation for the brightness temperature, you can see that there are various terms. So this is the again, the neutral fraction of hydrogen, and so it's on these kind of large scales. Remember, K of 0.1 is something like 60 megaparsecs, so it's fairly large scales. Maybe it fluctuates of order 10%. Density field similarly fluctuates by at most 10% on those scales. But then if you look at this temperature term, you have, so this is again, the CMB temperature divided by the spin temperature, which we can roughly say at these redshifts is corresponds to the gas temperature, right? So at redshift 10, the CMB is roughly 30 Kelvin, but the gas, is if it's adiabatically cooling as 1 plus Z, is 2 Kelvin. So you get a contrast of 10, 30, 10, 20 or so just from this one term. So this gives you a huge dynamic range, right? And you need this to be negative. You need this to be small to get this, because as the gas heats up, this term saturates to 0, so this term saturates to 1. So the largest dynamic range you get is when this guy here is much smaller than this guy. And so you need the universe to be cold. That's the punchline. But it's not a necessary and sufficient condition, because these are interferometers, so they don't measure the DC mode. You need some source of spatial fluctuations to piggyback on this dynamic range. So you can use any of the other terms to imprint spatial fluctuations, such as ionization fraction, matter density, temperature itself can spatially fluctuate, although we find that would require really, really soft SCDs to get enough power in the spatial fluctuations. So basically, you need the universe to be cold, and you need to have spatial fluctuations, in another term. And so these are kind of models that meet those 2 criteria. One is, again, this is the density field. This is a simulation where the gas is adiabatically cold, but their reionization is ongoing. So you can see the ionized regions as black here, and they're in a sharp contrast against the neutral gas. And so this sharp contrast of 0 and minus 300 gives you a large power, which exceeds the upper limits. Similarly, if you don't have any reionization going, and you just have the matter field here at low redshifts, just the matter fluctuations are sufficient, provided again that the universe is cold. So the matter field fluctuates large enough so you can still exceed these upper limits. So you need one or the other, and it's one of those things that you need both criteria to be met, right? It needs to be cold, and reionization needs to be either. So the interesting thing is it can't be in between these 2 extremes too much, because there's a cross term between ionization and density that ends up driving the signal down. So you need either matter dominant, you need something to set the fluctuations, and you need it to be cold. But since we've already know that the universe, I started off saying that we know roughly the EOR history, And at redshift 8, we know the universe is undergoing reionization. That means that this criteria is already fulfilled. So we do have fluctuations in ionization, which means that we can constrain the temperature of the universe. And so if you put this in a inference framework and you marginalize, you get a PDF on the spin temperature of the neutral gas, which looks something like this. Without Hera, you get this kind of orange distribution here, which has a lot of posterior mass here at low values, which are close to, this is the adiabatically cold regime down here in gray. But then when you add in the Hera data, suddenly these low values are disfavored. So you can ask also what is, so that's really cool. That's a new piece of data and something new that we can say about the thermal history of the universe at redshifts above 8 and 10. Yes.
Without Hera data, what was the prior year for
Yeah. So this is driven. So this is not reionization. This is the temperature. So this prior and this orange term depends on what your prior is on the heating history of the gas. So the shape of this orange curve is a mixture of what you get for the evolution of the star formation rate density and combined with the prior that you put on the X-ray luminosity to star formation rate from the galaxies, because we assume that the thing that's heating the universe are X-rays that are tied to star formation rate processes in galaxies. That's what we see locally. And then we choose a prior on that based on local observations of galaxies. And I'll show that in a minute. So the fact that there's a lot of prior volume down here is driven by this assumption of what X-ray efficiencies we see in local star forming galaxies. Does that make sense?
But I would have imagined that at that time already spin temperature is coupled and then
it is. The spin temperature is coupled, but that's a different process. The coupling is the UV. So this is the heating. And the thing that's doing the heating, at least in these models, are X-rays from star-forming galaxies. And so what the distribution is without Hera data depends on what prior you assume for this X-ray production. Okay. And I'll show that in a minute.
Can I ask a quick question?
There is no assumed contribution of AGNs because well, for a couple, it's a parametric model, so you can say that maybe the thing that's doing the heating is AGN, but it's parametrized in terms of the X-ray luminosity to star formation rate. So effectively, it's not, doesn't include AGN, which is something that we think is correct above redshifts of 5 or so, where AGN start dropping off very rapidly.
Can I ask
okay, so
question?
That's the mean IgM properties. What about galaxy properties? Well, as you might expect, again, it's 2 to 3 orders of magnitude above the detection. So the galaxy properties are not strongly constrained. These are the parameters that were used in this inference that I showed. And the without Hera, again, is orange. The with Hera is in purple. And so you can see the posteriors align for almost everything except this one parameter. And that is, if you zoom in, the thing I was just mentioning, the X-ray luminosity per star formation rate. Right, this is the PDF of this X-ray luminosity per star formation rate. And so our prior is flat over this range, and the posterior is peaked on this end. And the reason why the prior was chosen like this is because local galaxies are observed to sit here. Right. So including this range in our prior, these are the models that are sitting there at the cold range, so low values, but they're not that low. It's an order of magnitude weaker than local galaxies, right? If we shifted our range higher, then the prior would shift. If we shifted lower, it would go more down there. Okay. But we disfavor local values. And in fact, what I was showing is the first release. There was a second data release that included 4 times more nights of observations. And this is the result. And now you can see that the posterior is very strongly peaked beyond at these high values that are disfavoring the local galaxies at beyond 95% confidence limit. So even with these preliminary observations, we are, strongly disfavoring that the first galaxies looked like local galaxies, right? Which is really cool for something that's an upper limit that, is 3 times larger than 3 orders of magnitude larger than current data. So you can say, well, is this surprising? It sounds kind of surprising, right? But if you look closely, what local galaxies look like, these are local galaxies, the X-ray luminosity star formation rate of star-forming galaxies as a function of their metallicity. And so the populations kind of sit here. This is an empirical estimate, and this is a theoretical model by Tassos Fragos. So you can see that there's an increase in the X-ray luminosity as you go to lower metallicity. This is something that theoretically you expect because you see it observationally, but you also expect it theoretically because as you go to lower metallicities, winds start being less efficient in these binary stars. So the companion retains most of their gas, which then gets it was just able to be accreted on the compact object. And if you look at, so X-rays are more luminous for high mass X-ray binaries in low and metallicity environments, but then metallicity we know also evolves with galaxy mass. We see observationally that smaller galaxies are less metal enriched. That's something we expect. Metallicity is a cumulative process born from stars. And then if you fold those two things in and you say, well, what are the galaxies that are dominating the X-ray background? This is the thing that's heating the gas. This is the PDF of the X-ray emissivity at different redshifts, assuming 2 different kind of scaling relations. But basically at these redshifts, you get that the typical metallicities of galaxies are 10 to the minus 3, 10 to the minus 2, right? And so if I go back to this kind of X-ray metallicity versus X-ray luminosity versus metallicity diagram, the local galaxies sit over here, but the galaxies that we think are doing the heating are down here at metallicities below 10 to the minus 2. So the first galaxies we think sit down here. And these are kind of two of these estimates from the literature. And so if I go back to my PDF and I rotate it and kind of roughly put it on this plot, it actually sits very nicely in these kind of extrapolations that we get from local relations and theoretical models. So it's actually not so surprising, but it's it's actually from data instead of being theory. Okay, so if I have how am I doing on time? Oh, really? Okay, then I have time to finish. Okay, so then the last part of my talk, I'll talk about so that's the status. I'll talk about the future, right? The path to the revolution driven by this 21 centimeter line. All right, so as I said, now the current stage is at the level of upper limits. So every year, one of these collaborations publishes lower and lower limits. Again, it's a very challenging measurement. So in this regime, the things we need to know, obviously from an observational standpoint, we need to know the systematics. From a thermal noise standpoint, it's an easy measurement to make, but the thing that's limiting us is our systematics that are pretty challenging to analyze. So we need to both understand where they are in power spectrum space, if we can ignore them, mitigate them, and parametrize what we can't. From a theoretical standpoint, we need to know, do we have all the physics we need especially as I mentioned regarding heating sources. For example, if you include a significant contribution from these first molecular cooled galaxies, the constraints on this Lx over SFR weaken, but they're very strongly dependent on how efficient you assume is star formation inside these galaxies. This was shown in this recent work. Here, this is the constraint that I showed, but if you include, let's say somewhat reasonable assumptions, it weakens a little bit. And in really, really extreme models that have very strong star formation in the first molecular cooled galaxies, because their additional contribution obviously would heat the universe more, so we would weaken these constraints. The other thing to note is that the posteriors are prior dominated in a sense, which means that they depend on what you assume for your parameterization, unless we have realistic galaxy models that can then leverage other observations. So if you just use a 21 centimeter observation alone, because it's not a detection, you won't be able to constrain anything. The reason why we're able to constrain stuff is because we have complementary observations at high redshifts. And this is kind of an example that's shown in a paper by my recent student, where we kind of peeled off each term in the likelihood and show what happens. The prior here is shown in gray. So these are UV luminosity functions at 3 different redshifts. These are global evolutions of the 21 centimeter power spectra at one of these modes that's the most sensitive, the mean brightness temperature and the ionized fraction, so the ER history. So the prior is essentially just broad. You don't really constrain anything. But then when you include the UV luminosity function observations, suddenly you can see this collapse down because we have to reproduce the galaxies that we actually see. So that in blue, it doesn't affect too much any of the other observables, except to rule out like really, really extreme early ionizing models, because how this evolves tells us something about the star formation rate density as you go to higher redshifts. So you can't have crazy star formation models at really early times. But then now when you add in reionization constraints coming from optical depth and other measurements, now this thing shrinks from this blue region to this green region, and now we have an estimate of the UR history. And then with that, because as I mentioned, we need to have some fluctuations, with that, when we add in the Hera observation, the power spectrum now shrinks. The region goes from this green down to this purple, and the global temperature goes from this green down to this purple. So it's really the complementarity of these observations while we're still in this prior dominated regime that allows us to go into a likelihood dominated regime. Another thing about this current epoch is that emulators are useful. A lot of people are using emulators, and that's because the error when you're doing emulation is still subdominant to your other sources of error. And there's a bunch of papers that are doing that. Okay, so in a few years, where we hope to be is to have a low signal detection of the power spectrum, maybe at a couple of redshifts. And actually, the current Hera data season that's just finished has enough clean data, unflagged clean data, to be able to detect the epoch of reionization in the power spectra. Right, it's not saying that we will, but it's saying that the data, the amount of clean data in terms of signal to noise is there to do that. But even if that doesn't do it, in a few years, we're bound to have some low signal detection. Because again, the signal is there. It's not like we're looking for some exotic physics, right? This is different from, if you're in particle physics and you think that there's a particle in it, there's not a particle. The universe is there. We know that the signal is there. So it's just a matter of actually observing it. And so again, we also need to understand systematics. So this thing is still here. But in terms of interpretation, what we need is to convince ourselves that the signal is real, because we and others are not going to believe that it's real unless we can cross-correlate it with something that we know is of cosmic origins. And basically it's something that, you know, is generally done. It's been done at low redshifts using the CHIME collaboration. The first detection of low redshift 21 centimeter was in the cross signal, but at high redshifts, basically any source of any tracer of large scale structure will cross correlate because the radiation fields are sourced by galaxies, which are biased sources of large scale structure. And so there's many choices for cross correlation going from cosmic backgrounds. These are hard because this is an integral constraint. The more promising are resolved galaxies. There's several surveys possibilities here, and intensity mapping. Also, a few instruments are going at higher redshifts, like CCAT prime, for example. So I won't obviously go through that list. And then finally, in a couple of decades, where we hope to be is this high signal to noise map of the observable universe, which will come from this SKA low square kilometer array telescope that's being built as we speak in Australia. And so I think this data set will be insanely valuable from all sorts of, and I'm sure we have not even discovered its full potential. So there's still a lot of time to do that. As I mentioned, the square kilometer array is being built. And by the end of the decade, it will start accepting key science projects, taking preliminary data already in the next couple of years, and then taking commissioning data by the end of the decade. So in this regime, what we need to worry about different things from an interpretation standpoint. We'll start thinking about what is an optimal compression. What I've been showing so far, power spectrum. Power spectrum are easy things to measure. They get a lot of signal to noise because there's a lot of compression here. But the signal, unlike the CMB, the cosmic signal is highly non-Gaussian, right? And so the cosmic signal, the power spectrum for a non-Gaussian field is a lossy compression. You waste some information. So we need to start thinking about what can give us the most bang for your buck, to speak. Do we actually need to know the likelihood analytically? Another really exciting thing, I think, is this field of simulation-based inference that started to pop up and being used in 21 centimeter. And so the idea in simulation-based inference is that if you can sample kind of all relevant sources of stochasticity, including cosmic, the cosmic seed, thermal noise, then you can, each forward model is essentially a pull from your observed data distribution. And so you can actually you can train density estimators to fit the likelihood using some training set of mock observations. And in fact, you can do this with a factor of few to 10 times fewer simulations that you might need in a traditional MCMC or nested sampling inference. And the cool thing is then again, the likelihood here is not explicit, and the likelihood for, we're all kind of playing fast and loose with the standard chi-squared likelihood when we do this, but the likelihood is not a chi-squared in these fields. And here you get the likelihood for free because you're fitting it. The other interesting thing, very exciting thing, is using these kind of generators to emulate maps instead of just emulating the power spectra. This is some recent work showing some 2D, at least, map emulators, which we need to understand how well do we trust these emulators, but it is potentially pretty exciting. And we actually need to understand fundamentally how well we trust our simulators, right? That's something that we don't care too much about at the moment because, the error bars are pretty large. This is an example, for example, from 21 centimeter fast, and this is a rate transfer simulation. So you can say, okay, they roughly agree on large scales, but obviously if you look closer on small scales, there are definite disagreements. and these might start limiting our ability to extract information. That's something that we need to quantify in the future. All right, so let me conclude here. So I mentioned the cosmic signal will allow us to learn the average properties of the bulk galaxy population, the typical galaxies that we'll never be able to see directly. And already the upper limits on the power spectrum show us that there was some heating of the IGM happening before redshift 10. And if this heating was provided, as it is in local star-forming galaxies, by high-mass X-ray binaries, that means they need to be more luminous than the local sample. Future detections will need to be cross-correlated with something of known origin, so we need to start looking at what are complementary surveys. And then finally, when we have high signal-to-noise maps, then we will need to start thinking about these kind of big data questions that are also exciting on that standpoint. So yeah, that's it. Thank you very much.
More questions?
Do I? Hamza? Hi, Hamza.
Hi, Andre. Thanks for the really interesting talk.
Do
I
I
had
need
a
to do something?
question actually on the orange line. Are you able to hear me?
But my volume is on, so what do I need to do?
Oh, okay. Are you able to hear me?
Oops. Yes.
Okay. You can hear me, right?
My volume. Yes, I can hear you. Sorry.
Okay, great. No problem. So I had a question on that orange curve you showed a few slides ago on the Hera with and without Hera with the priors, where you showed like it was, yeah. So yeah, thanks for that really interesting comparison. It was also the previous one, I think, the one which you had two peaks. Yeah, exactly. So I was just wondering, is this first thing with the lower peak, which is like subdued? When you say without Hera, do you mean all other experiments, including paper and other things which came before Hera?
So we don't. Sorry, we don't use other 21 centimeter experiments because they will not change anything because they're higher constraints. So we show that in the paper that including other 21 centimeter experiments doesn't affect it. We only use the most constraining one, which is Hera. So the without Hera instead includes those terms that I mentioned subsequently when I was showing the different likelihood terms. So it includes UV luminosity function observations and EOR history constraints from the CMB and other sources of EOR history constraints.
Okay, and so if suppose you used maybe the other experiments, I'm wondering because this peak is very different from the one you got at Hera. They're so far apart. So maybe would it like push it towards the right a bit? I don't know. I was just wondering.
Okay, so you're saying that if I labeled. Okay, yeah, I see what you're saying. Yeah, this could be instead with 21 centimeter without 21 centimeter, I guess is the way that we're thinking about it. Yeah, you're right. If I included other without Hera, but other 21 centimeter, then this might shift a little bit. We haven't checked that. What we have checked is that the purple posterior does not change with the inclusion of other 21 centimeter because this is the current kind of record holder.
Yeah. Oh, okay. Thanks a lot.
No worries.
So you just said, so one of the conclusions was that the luminosity at the same time needed to be more luminous. But is it saying something about an expansion? Not the very first topic.
Yeah, so I think that is that is one of the kind of exciting kind of conclusions that one could draw. we don't know at this point because we don't have enough data to say anything beyond essentially this one kind of parameter that parameterizes the combination of these things. So you could imagine that in the estimates that I've shown here, so these are this is just an empirical relation. But this is a theoretical model. Actually, the blue thing is a theoretical model here. The dashed line, sorry, is a theoretical model. Here, the thing that was varied was just the metallicity of the sample, but not the initial mass function. So if you had an initial mass function, that could result in some additional bump down here as you go to different mass. So it could contribute to that. But we're not at the stage to be able to kind of disentangle these kind of things. You would need to build up a more sophisticated model, which we have. Actually, we are doing that, but we also need more data to constrain that model, which we don't have at the moment. With the detection, we have a draft of paper. With the detection, we should be able to actually distinguish between a few of these things, because then you can actually trace this evolution through time, and they have different redshifts evolutions.
Yeah, I think the thing you showed with the Pico prospects for SKA is wonderful and films in volume. But I was wondering about this, what to call it, a dark corridor where the brightness temperature crosses. I think the CMB, if I understood correctly. Is this a region of no data, or is it are the fluctuations there that you can still pull out? Or?
You mean in the light cone?
Yeah.
This?
Yeah, or not.
So you're talking about this? So this, yeah, there's plenty of data. Actually, this is where, this is roughly where the power spectrum peaks. Because you have a huge contrast between regions that are still cold and regions that are hot. So there's a huge amount of data here. And so the power spectrum evolution, which I don't have on this plot, but the power spectrum evolution, you have strong power all those throughout this kind of range. Yeah. It's so the black is the mean, right? But if you can do a Fourier transform by eye, there's a lot of power here.
Another way is gravitational waves. So I was just wondering myself, is there some kind of synergy with gravitational waves?
Well, yes, in theory, things like the X-ray binaries in theory would make gravitational waves, right? When they coalesce. I think in practice, it's very difficult to connect gravitational wave observations to these kinds of signals, because we're not spatially locating things, right? So it's not like nearby with, some future instruments, we're going to be able to have some decent spatial resolution. For these early times, you would need to really rely on your models of the cumulative kind of density function, the distribution of gravitational waves that you get. So you could imagine leveraging these quantities in some way, but it would involve, I think, a lot of model assumptions when you do so.
Depending on the physical distribution, which kind of makes which grounds on certain redshifts, or is it not, or is it kind of a
radio frequency interference, you mean? Yes.
Is it
Yes, so it's local. Most of this is in the FM band, right? So there are radio channels. Most of the experiments operate in regions that have low RFI. That's why they go to deserts in Australia and South Africa. But LOFAR is able to operate in the heart of Europe, without too much problems. And the reason is, as you said, it is confined to certain bands. So they flag the bands that they know they have. Sorry. Yes, they essentially know some of the bands. There was recent data that showed these Starlink satellites being really annoying in some of the bands. So there are some things, but those are transients, which you can also flag by the fact that they're not there in one data set versus the other. So there's a lot of data cuts that you can do, which means that RFI is not the limiting source of, at least at this stage. Maybe in the future high signal to noise detections, that'll be the limiting concern, but right now it's not.
Okay. Second question would be more data. I mean, basically, all these constraints are kind of check to assume that noise is power spectrum seeing is not.
Yes. Yes.
Do you see like the noise is going down expected? More data. I guess the thermal noise.
Yes. So you do see for Hera, and that's a good question. Like because for Hera, we do see going from this first data set to the second data set, we do see a decrease that scales with the noise in the region. Again, it's a very different observation than something like LOFAR. Hera is really designed to maximize your signal to noise in a compact dish array, compact array. So you have a lot of baselines that are probing the same modes on the sky. And so it usually does what's called foreground avoidance. So it just throws out regions that we think are contaminated, whereas something like LOFAR has more of an imaging setup. And so they really tried to kind of dig out some stuff under the foregrounds. And so LOFAR's recent releases that are in prep, from the stuff that I've seen, they don't go down to the noise. And so there was a recent conference where I asked pretty much the same question. Well, why are you calling these upper limits? You detected something, right? Because it's above the noise. So you detected systematic. So it's a little bit of in that sense, it can be a little bit of just a marketing or like a point of view type thing. But in these data sets, we do scale with the thermal noise.
Okay, so I guess we can stop here. If anybody has questions or wants to talk, one day over the afternoon, here today.